Hello, everyone.
Right, welcome everyone. So today is the last Neuro-Symbolic Wednesday for a few weeks as the build up to the summer school. So let me, are you seeing my slides?
Yes.
Okay, great. So as usual, reminder about the different ways you can join us, different places. You can meet us. All right, if you haven't seen this before, grab the QR code. You can work with us. Just have a chat with us about your interests, and we can see. We're building a system which has many aspects to it. So if you're interested in that, let us know. Or if you're building your own system, that's great too. We can help you advertise it, and whether it's good quality code, hopefully for your paper or something else, or a bigger system, let's chat. And if it's something we think fits and we can help you actually get visibility for it, we can host it for you. And even get people to work on it. Okay, still no one's taken us up on presenting their work that's not their own reading group style, but if you're interested in that, it's still open. And other things, hiring. If you're a startup, we can help advertise you. This is free, just helping the community. And if you want to donate, we will be ecstatic. Or volunteer your time helping with this meeting, summer school, educational stuff we're doing, anything. We need lots of help. Okay, just a reminder, we have an hour and Q&A is through here, just to jump ahead, Discord, YouTube, or LinkedIn, and then hopefully our speaker, if she can may jump on Discord to answer any other questions. Okay, so and big reminder, the summer school is coming up August 6th and 7th, and we're gonna find a way to reward people for signing up. Friends, at a minimum, you will get props from us publicly if you sign up a lot of people, but we're thinking of some other additional thing. But please spread the word is the point. Okay, luma.com/Neuro-Symbolic Summer School 26. Okay. And without further ado.
Sorry to interrupt. I just want to remind everyone, just in case there are new people here, summer school is free and remote event. Similar
free, yes, and remote. You just have to sign up for it, and that's it. Okay, we're a nonprofit. This is for the community. Nobody has to travel. Okay. All right, so without further ado, Giulia is going to tell us about Neuro-LENS, and we're also joined by our supervisor. Here's a bit more about Giulia, and you can check out her other works and her website. Okay, and she's speaking to us from Sweden. So just a reminder, this is a global event. The summer school will be particularly global with speakers from all over the world. Okay, and here's the final kind of reminder about the summer school. Okay, with that, take it away.
Thank you for the introduction. Thank you for having me. I'm going to share my slides. All right. So today I'm going to talk about Neuro-LENS, a neuro-symbolic framework which integrates incomplete background knowledge and deep learning. The talk of today is based on two papers. The first paper was published in last year's NESI conference. The second paper is an extension of the first paper, and it was recently accepted for the Neuro-Symbolic Artificial Intelligence Journal. Both papers were written with my co-authors and supervisors, Veselka Boeva and Elena Tsiborkova. In these papers, we try to tackle two big challenges that are encountered when dealing with real-world data and or industrial use cases, namely dealing with the ambiguity and uncertainty in the data and dealing with the injection or integration of background knowledge into deep learning models. We tackle these challenges leveraging the combination of two building blocks, a neural component, deep learning based, and a symbolic component which exploits model logic and evidence theory. I'm going to talk more about these two building blocks and the various combinations of the two that we proposed in the papers later in the presentation. First, I'd like to have a short introduction about evidence theory and model logic. Then I'm going to explain how we went from theory to applying these concepts to real-world use cases. I'll introduce the Neuro-LENS framework, and then I'll go a bit more into details in two use cases we validated the framework on: an abandoned object detection use case and a vehicle failure prediction use case. And then I'll conclude with some remarks on the work. So evidence theory, or Dempster-Shafer theory, was developed by Dempster and Shafer in the 1960s, 1970s. It is a mathematical framework which deals reasons with uncertain information. It is a generalization of probability theory, and I think a comparison with probability theory will make the main concepts more clear. So in probability theory, we have a probability mass function, which assigns a probability mass to a single hypothesis, while in Dempster-Shafer theory, we have a basic belief assignment function, or a mass function, which assigns basic belief masses to a subset of hypotheses. So we have a multi-valued mapping between evidence and a subset of hypotheses, which is a subset of what is called in Dempster-Shafer theory the frame of discernment omega. And this difference between single hypothesis and a subset of hypotheses makes it possible for Dempster-Shafer theory to deal with ignorance. For example, in probability theory, if we have two possible hypotheses, A and B, if we assign a probability mass of 0.5 to each A and B, we will not know whether A and B are equally likely, or whether we have no information to prefer A over B. In Dempster-Shafer theory, in the same scenario, we would just assign the whole belief mass to the entire frame of discernment, which in this case contains A and B. So what that means is that the only statement that we will make is that with the available evidence, we can only say that the true hypothesis is among A and B. So given our multi-valued mapping, the basic belief assignment, we can define two complementary measures, plausibility and belief, which are computed by constructing the inverse and super-inverse images of the belief assignment function. The inverse image is used to construct the plausibility, measure, and it is basically the maximum amount of evidence support that could potentially be assigned to a subset of hypothesis B. And it includes all the evidence that is not incompatible with B, which is obtained by summing all the masses of all subsets with a non-empty intersection with B. The superinverse image is used to compute the belief measure, and it is the minimum amount of support that can be unequivocally committed to B. And it is obtained by summing the masses of all subsets which are entirely contained in B. So given belief and plausibility, we can define an interval, the lower bound of which is the belief, and the upper bound of which is the plausibility. And we can say that the actual probability of B being true must lie within this interval. Model logic is an extension of classical propositional logic with additional model operators, which are used to reason about statements which are true depending on a particular context or interpretation, rather than being universally true or false. So the additional model operators are possibility and necessity. So we say that given a set of worlds which are to be intended as a state of affairs or possible scenarios, we have that a proposition P is necessary if it is true in all possible worlds. And we can say that a proposition P is possible if it is true in at least one of these worlds. Then we can define the truth set of a proposition, which is just a set of all worlds in which a proposition is true. For example, if here in the picture we have all the W's are different possible worlds, and if we were to define the truth set of the necessity of P, it will just be W4, which is the only world in which P is necessary. So we can build a bridge between evidence theory and model logic by framing evidence theory in model logic. So by defining plausibility and belief on a set W in terms of possibility and necessity, then we will just define the plausibility of B as the ratio between the true sets of the possibility of B and the possibility of the whole frame of discernment. And same thing for the belief. We will define that as the ratio between the truth set of the necessity of B over the possibility of the whole frame of discernment. And this was defined, derived in the two papers cited at the bottom of the slide. So how do we go from these theoretical concepts to practical application? To do this, we developed the symbolic component of Neuro-LENS, which takes in data, input data, which can be of different types. In the use cases that we are presenting, we had images or tabular data. And then binary attributes are extracted from the input data. And here, to show a correspondence with the previous concepts, here the binary attributes will be the evidence. Then we construct a multi-valued mapping, so a basically belief assignment from the binary attribute space, so the evidence space, to the hypothesis space, which are the samples in our data set. And based on this multi-valued mapping, we can define the possibility and necessity conditions for our samples. Using the evidence theory framed in model logic formula, we can compute plausibility and belief measures using the possibility and necessity conditions that we derived. And if we combine the plausibility and belief measures into a single score, we have a score that gives us a likelihood of the input samples to belong to a certain class that we are characterizing. Or again, we can stop at the possibility and necessity rules and obtain rules, evidence-based rules, conditions that a sample has to satisfy to be classified in a certain class that we are characterizing within the component. So as I anticipated, the Neuro-LENS framework combines two building blocks, the symbolic component that I just introduced, and a neural component, which is a deep learning model that can be adapted to the use case at hand. We explored three different combinations of the neural component and the symbolic component, a neural to symbolic chaining, where the raw data is fed to the neural component, to the neural network, which extracts attributes, which are then used to the symbolic component to perform the final classification. And this is relevant when the data type cannot be directly processed by the symbolic component, for example, in case of images. In the symbolic to neural chaining, we start with the symbolic component. So the background knowledge data is fed to the symbolic component, which extracts features based on model logic and evidence theory, so the possibility and necessity rules and the plausibility and belief scores. Then these features are fed as extra features to the neural component in addition to the raw data. So the neural component has now the raw data and also the background information to perform a more accurate classification or forecast. And this is useful when the use case requires integrating data of different types. Then the third combination is the parallel neural symbolic integration. So where the neural component and the symbolic component work in parallel. Again, the raw data is fed to the neural component. The background knowledge data is fed to the symbolic component. And then a rule-based classifier combines the outputs of these two components for the final classification and forecast. And this allows to employ the most suitable model for every data type while retaining the interpretability provided by the symbolic component. So now I'm going to go a bit more into details on the two use cases that we validated our framework on. The first one is a scene classification task for abandoned object detection. The second one is vehicle failure prediction. So scene classification. Scene classification task is meant by categorically classifying scenes from static images, for example, in our case, frames from surveillance videos. It is a challenging task due to the complexity and variability that we encounter in real-world situations, which are also inherently semantically ambiguous. And an additional challenge is that it's difficult to find high quality and diverse data sets because of privacy constraints and because of how labor intensive it is to label these images, these data sets. In our work, we used two data sets, that's 2006 and ABS 2007. They both depict realistic scenarios of luggages being abandoned in train or metro stations. They are pretty small data sets, especially the IBS 2007, and they're also imbalanced. So the abandoned luggage, the images containing abandoned luggages are the minority cause. For methodology, we use the neural to symbolic chaining. So first we have the neural component, which is simply two pre-trained deep learning model, an object detection model, and a depth estimation model. And we feed the outputs of these two pre-trained neural networks to the symbolic component, which performs the same steps as I explained before. So we characterize the images by extracting instances, attributes from the outputs of the neural component. And these are our evidence. We construct the multi-valued mapping between the set of instances and our data set, our samples, our images. And then using model logic, we can derive necessity and possibility rules, which can be used to construct a rule-based classifier, or we can compute belief and plausibility measures from the necessity and possibility rules to build a score-based classifier. The neural component, as I said, is formed by an object detection model and a depth estimation model, both pre-trained. The object detection model returns labels, class labels, and bounding boxes for each object detected in the image. The depth estimation model returns estimation of depth for each pixel in the image. Then we use the bounding boxes to get estimation of the depth of each object in the image in order to have a more accurate idea of the relative position of objects in the image. Then these outputs, so the class labels, bounding boxes, and depth estimation are used to extract binary attributes that give us information about the objects present in the image and the relationship between these objects. For example, whether there is a bag or whether there is a person in the image, or whether their bounding boxes overlap, if they overlap partially, or if they are completely overlapping. Then we build our inverse and super inverse images from the set of binary attributes to the set of images. So for example, here we have the no overlap attribute, and we map it to the set of images in our data set where we have no overlap between a person and a bag, between their bounding boxes. And since the intersection between this subset and the subset of images that contain an abandoned luggage in the dataset in red, we say that having no overlap between the two bounding boxes is a possibility condition for that image to contain an abandoned luggage. Equally for the super inverse image. So for example, here we have the attribute, the image contains a bag but no person. And if we map that to the subset of images in our data set which contain an abandoned luggage, we see that this image is entirely contained in the images which contain an abandoned luggage. So then we can say that this is a necessity condition, like a necessary condition that an image must satisfy to contain an abandoned object. After we derive these rules, we can construct a rule-based classifier, which takes as input an image. Then it verifies whether this image satisfied the necessity conditions for the positive class, the positive class being images containing an abandoned luggage. If these conditions are satisfied, then the image is placed in is classified as belonging to the positive class, so as containing an abandoned luggage. If the image satisfies the necessity condition for the negative class, so for images not containing an abandoned luggage, then it is placed in the negative class. It is classified as negative. If none of these two are satisfied, the image is placed in a third class, known of known class, which basically means that we don't have enough evidence to classify that image with sufficient certainty. This avoids having misclassifications. It signals uncertain scenarios for the images that are placed in the known of known class. You can see here the results where I distinguish between the detected positives and negatives and the images which are placed in the known of known class. The performance is quite better for the PETS 2006 dataset than the ABS 2007 dataset, which is much, much smaller. So classes are not sufficiently well characterized in this smaller dataset. Then if we calculate plausibility and belief, we can build this score-based classifier. Here, the plausibility and belief are combined into a single score, which calculates basically the ratio of available evidence supporting the positive class normalized by all available evidence. And this allows us to have a more granular quantification of the risk of having an abandoned object present in the scene. But you can see the ROC curve here of the results where a threshold, a movie threshold is placed on the score values. The performance is still worse on the AVS dataset because, again, it is smaller and the classes are not, the variability of scenarios doesn't allow to properly characterize the classes. So now I'm going to talk about the second use case, vehicle failure prediction. Predicting failure in assets in general, and also in vehicles, helps with maintaining the asset's reliability and performance, and also helps with limiting repair costs and potential delays due to unexpected failures. It is, again, a challenging task because it is hard to find real-world data sets, and the data sets that are available are very, very imbalanced. We worked with the Scania dataset for our work. It consists of two types of data: multivariate time series data collected by sensors placed on board of the vehicles, and technical specifications data of the vehicle, for example, the engine type. We have data from over 23,000 vehicles. And as you can see here in the tables, it is quite unbalanced. We have less than 10% of faulty trucks in the training set, and in the validation and test set, it's less than 3%. In the paper that presents this data set, there are class labels available, which are discretized according to the time left until failure. So we have 5 classes from 0 to 4. Class 4 means that there are more than 48 hours left before the truck incurs into failure, the vehicle. And class 4 means that the failure will occur within the next 6 hours. And again, you can see how unbalanced the data set is. So here we applied the second and the third combination of the 2 building blocks, neural component and symbolic component. The symbolic neural training. So here the specification data, which specify technical specifications of the vehicles, is fed to the symbolic component. The symbolic component extracts features, which are fed to the neural component together with the time series data collected by onboard sensors in order to perform the final classification or forecast. Then in the parallel integration, we have the operational data, again, time series data fed to the neural component, and the specification data fed to the symbolic component. And then the output of these two components is combined in a rule-based classifier. The symbolic component is the same as in the previous use case. The data that we feed to the symbolic component is different. Now we have tabular data, and we extract binary attributes from the tabular data, the specification data of the trucks, the vehicles. Then we construct, again, our multi-valid mapping between the evidence, which are the attributes that we derived from the specification data, to the samples in our data set. We define, again, the possibility and necessity rules, compute the plausibility and belief measures from the possibility and necessity rules, combine them into a single score, and then we obtain as output both evidence-based rules and evidence-based scores. And both of them represent the predisposition to failure of a vehicle. So a few examples. Again, as before, we compute the inverse and super inverse images. Inverse is connected to possibility and plausibility. Super inverse is connected to necessity and belief. And since we have several specifications for each vehicle in order to also consider the possible interactions between specifications. We consider both single specifications, and then again, for example, the engine type is A. We map it to the samples in the data set which have engine type A and see if the intersection between these subset and the failing vehicles or the non-failing vehicles, depending on which class we're considering, is non-empty or whether it is completely included in the subset. And again, to consider also the interactions between specifications, we also consider pairs of specifications and also triplets of specifications. So here we map all the vehicles, we map these two specifications to the vehicles that have both engine type A and wheel type C. This is what we get when trying to classify the vehicles into failing or not failing, solely using the specification data. So solely based on their technical specification. Here, the score is the same score that we use in the image use cases, object detection use case. So it's just plausibility and belief combined into a single score, which indicates the likelihood of failure based on the technical specifications of a truck. So here you see that the performance is not great, but it's definitely better than a random classifier, which is the diagonal line. And the performance is definitely not meant to be perfect because we are not considering all the data. The important thing is that it's better than it is contributing to the classification. So, of course, we need to look at the time series data because the failure will depend mostly on the usage and the time series data extracted by onboard sensors. So the first combination that we explored in this use case was the symbolic neural training. Again, specification data is fed to the symbolic component, which extracts features which give us information on the predisposition to failure of a truck. Then the extracted features are added as extra feature to the neural component, that in this case is an LSTM network. So the LSTM takes both the time series data from onboard sensors and these extra features extracted by symbolic component and provides the final forecast. We take as input 12 consecutive time steps, a window of 12 time steps, and then we output the prediction of the next 12 time steps. So we predict class 0 through 4, which, as mentioned before, indicates the time left until failure. So class 0 is normal conditions, so there's more than 48 hours until the failure. Class 4, there's an imminent failure. The failure will occur within 6 hours. So here you can also see the effect of the imbalance in the data. Class 0, the normal condition, is over 90% of the data. So if we compare our model to only using operational data, so only looking at the time series data without considering the specifications of the vehicles, we see that the performance doesn't vary much for the normal conditions. But if we look at class 4, so being very close to failure, then the model that only takes the operational data, the sensor data, which is this blue line here, cannot detect any failing vehicles, while introducing the background knowledge as additional feature to the LSTM greatly improves the results. And here I'm showing the F1 score for class 0 and class 4, and also the precision here. The second combination that we explored is the parallel neural symbolic integration. So we feed the time sensor, the time series data from onboard sensors to the neural component, which in this case is an LSTM autoencoder, and then the specification data is fed to the symbolic component. The LSTM autoencoder is simply trying to reconstruct the operational data. So the output of the neural component is the reconstruction error of the LSTM autoencoder, which is trained on normal conditions. So if an asset goes towards failure, the reconstruction error should increase. And the rule-based classifier uses a simple logical formula to output the final result. So if the reconstruction error is higher than a certain threshold, and the plausibility of the positive class, so failing vehicles, is higher than a threshold Y, where X and Y are chosen based on the distribution of the validation data. And if there is any belief measure assigned to the positive class, then the rule-based classifier detects a failure. Here are some results for the parallel Neuro-Symbolic integration. At the top, you can see only the results of the LSTM autoencoder. So this is the average reconstruction error, distinguishing between failing tracks in red and non-failing tracks in blue. You can see that already just looking at the reconstruction error, there is a difference between failing tracks and non-failing tracks, although this is an average value. So yeah, the results for single assets is can vary quite a lot. And at the bottom, you can see the cumulative percentage of failing vehicles detected with different time horizons. So either predicting whether there is a failure in the next time step, in the next 6 time steps, or in the next 12 time steps. And as it is intuitive, the performance decreases as we look at a longer time horizons. To have a better idea of how this parallel Neuro-Symbolic integration model works, we compared it with models that were published in literature, which are purely deep learning based models, which were only trained on time series data. So they didn't consider the specification data, given the challenge of integrating them into the neural network. And you can see that adding the symbolic component to the approach allows us to outperform a more complex deep learning architecture, even using a simple LSTM autoencoder. So to conclude, I presented Neuro-LENS, a framework which combines a symbolic component and a neural component in 3 different ways. It is modular in nature, which facilitates the integration of symbolic reasoning and deep learning, and allows for greater flexibility and to generalize across various use cases and data types. The explainability and interpretability, which are very important in practical applications and especially in industrial settings, are provided by the symbolic component and for the use rule-based classifiers. And it captures both uncertainty and imprecision thanks to model logic and evidence theory, which is again very important for real-world scenarios and industrial settings where we are often dealing with noisy data and incomplete background knowledge. Thank you, and I'm ready for questions.
All right. Thank you so much, Giulia. Let me now introduce also, we have Veselka Bova and Elena Siporkova, Giulia's supervisors. So here to help with questions and advanced discussion. So thank you for joining. Go ahead, Olga, any questions?
Yes, thank you very much, Giulia, for your presentation. Okay, let me check questions. I don't see it. 1 second. Yes, I don't see any questions on YouTube. Let me also check Discord. Yes, okay, we have one question on Discord. Provided one would like to integrate multiple huge data sets of heterogeneous nature, like for example, volunteer applications aim to do, what do you think your LENS framework would scale?
So if I heard correctly, you want to integrate several huge
Multiple
data sets?
huge, yes, provided one would like to integrate multiple huge data sets of heterogeneous nature. What do you think your LENS framework would scale?
I think it really depends, well, on the use case and the type of data, but the symbolic component is quite light computationally, and all the heavy work that might be needed can be done offline. Again, it depends what you're trying to do with these data sets, but I think that the scalability will mostly depend on the neural component. So you might have to do some work on optimizing the neural component to make it scalable, but it is definitely feasible in the framework within the structure.
Thank you.
Yeah.
And then, do you see the potential of your evidence-based rules to surpass state-of-the-art methods?
I mean, state-of-the-art for many use cases is purely deep learning models nowadays. I think it is possible. I think one important thing, especially in real-world application and industrial settings, is not just pure performance, but also interpretability and robustness. So it depends on how you define surpass state-of-the-art. I think you always have to look at the trade-offs. So maybe performance won't be extremely significantly higher, but then you gain in interpretability, which might make the difference in a model actually being used or not used in an industrial setting.
If I might add here,
Please.
I think even Giulia is very modest, because for the truck database, we surpassed the state of the art, and it was a data set that was published for a competition by Scania, and practically nobody that used it so far used the technical specification data. Everybody jumped on training sophisticated neural architectures on the time series data. So in a sense, we surpass it by kind of very optimally exploiting all the available data, which in industrial use cases sometimes is a really luxury, and it is really pity to let it lie around and not use it.
Yeah, I was going to say, I think Giulia effectively showed she beat the state of the art at her table, at least.
Yeah. And then I have a follow-up question from myself. So I'm not sure if I missed it, but Giulia, maybe can you show a couple of examples of interpretability and explainability for the use cases that you showed? So I think you mostly focused on like accuracy, like what exactly is interpretable and explainable part in your models?
For example, in the abandoned object detection case, you're really basing your classification on the possibility and necessity conditions. So for example, if the image is classified as containing an abandoned luggage, you can look at the possibility and necessity conditions which are satisfied by the image and say, like a simplistic example, this image is classified as containing an abandoned luggage because there is a bag in the image, but no person is detected in the image, or because there is a bag and there is a person, but the distance between them is large enough that we can say that that bag doesn't belong to that person.
Okay, thank you. How about the other data set?
The other data sets, it's a bit more tricky because you have also the operational data, but you can state that it depends on the combination that you're using, but like you can look at which technical characteristics are contributing to the failure. So then the industry, the company might say this engine type is a big factor in leading to a failure, like trucks which have this engine type incur in failures more frequently than the other ones. Maybe we should look at this engine type. So that would be significant, like valuable information given by the model. Also in the rule-based classifier, you can also distinguish between the contribution of the time series data. So like how much the failure is caused by the usage, how the vehicle was used, and how much it depended on just the technical characteristics.
Okay, thank you. Okay, meanwhile, we got a few more questions from the audience. How would strategy 2 be used for transformers instead of LSTM?
I mean, I think it's the same concept. I think, as I said, the modularity of the framework is a point of strength. You just swap the LSTM for a transformer, and you just have that extra feature, and it might perform better. But yeah, it's really within the modularity of the approach.
Thank you. A quick comment to our technical side. Joe, could you please also show question on the screen while I'm reading it? So, okay, the next question we have, what about training zero-knowledge proof caches to improve inference speed?
Zero-knowledge proof. So like a zero-shot inference. I'm not sure.
Okay, maybe we can
I know what they mean.
But maybe just answering with question, why would you do that? I mean, we don't have problems with inference speed, right? At that stage. So, and we have sufficient background information. Practically our method is the benefit is that we actually inject background knowledge in the neural model. So why would we want to do it with zero knowledge, whatever it means?
Okay, thank you. The next question we have, was there a F1 precision recall score computed for other neural baselines and Neuro-LENS on the drug data?
Yeah, sadly, I think it's referring to the comparison with the other neural baselines. Yes. Sadly, the papers only reported the accuracy, so I can only compare the accuracy. It's not great in this use case because the data set is quite imbalanced. So the accuracy is basically mostly driven by the majority class. But no, the accuracy was the only metric reported. So that's why the comparison is on the accuracy.
Okay, thank you. A quick side question, if the slide deck can be available, do you think you can share the slides with our audience on Discord?
We'll think about that because we work on industrial data, so we'll give it a thought. Okay.
Yeah. Okay. Thank you. Okay, for future research, would you consider introducing more conditions besides possibility and necessity?
Well, I think in model logic, you have possibility and necessity. What will be useful, I think, is adding more attributes. So more ways, more attributes you can compute your possibility and necessity on. And then also with belief and plausibility, you have a score instead of a binary value. So you can also get a more granular value measure of how possible or how necessary a proposition is. So I think more than adding more conditions, it is very good, and it brings definitely improvements to a use case to add more attributes. So more evidence.
Okay, thanks. And one more question from Discord. When generating huge rule sets, how would you handle inconsistencies? Did you encounter some in your experiments?
Well, actually, handling conflicting evidence is already like a defined concept in evidence theory. So that will be just applying that part of the theoretical knowledge. Did I encounter conflicting evidence? No, but again, in different use cases, when you have to take that into account, there is a theoretical background that allows you to do that.
But actually, if you consult our articles, we have a measure of ambiguity. So practically, any conflicting rules are captured in this measure. So dealing with evidence theory allows, of course, to manage this such type of situation and deal with uncertainty. So it just Giulia didn't have time to present the ambiguities.
Okay, thank you very much. So far, these are all the questions from the audience. Alex, do you have any comments or questions from your end?
Yeah, just first comment is, we scan the literature, and it's growing rapidly, the Neuro-Symbolic literature, to curate things to show here, Neuro-Symbolic Wednesdays and the summer school. And I don't know, maybe we looked at 500 papers or something published in the last year all over the place, all conferences we can find. I think I like here the use of more expressive logics. There's another camp within Neuro-Symbolic that says, that believes you should use less expressive logics because of, mainly because of inference speed. So I want to bring up the inference question. So we like to show the whole spectrum, anything that illustrates a corner of the Neuro-Symbolic world that I think is not shown enough. We'd like to show it. So in particular, modal logics, this is where things get fancy and higher order and so on. So, but inferences, but I think you're not really doing, so my general question is about, doing logical inference with this, expressive logic. But it seems like you're not really having to do that because they're really just, rules that you apply, you don't have to do a chaining of things. But any comment on that? Like, will you ever have to do inference in your method, or do you plan to? And if so, what would be the inference, algorithm?
So again, I think it really depends on the use case and what you're trying to do. In our case, basically for the vehicles use case, the goal was just to extract background knowledge that, in a way, that a neural network or that could be used further in the method. Yeah, I think our method is also, our vision is also quite driven by the fact that we work on industrial use cases.
Okay, yeah, it's a topic we could talk more about offline. We actually do.
I think you're correct. We don't do now inference, But it was just first attempt to demonstrate that putting these concepts together can just give a benefit. But eventually, if we start introducing time and then move to temporal logic, maybe we'll get some more complex situations where we'll need to do inference.
Cool.
We're looking toward this extension.
We have some work kind of adjacent to what you're doing on doing inference in probabilistic logics with bounds, like an extension of creedal networks. But anyway, where we do work out how to do the inference, and so there might be something, interesting to think about. You have a more expressive semantics actually than we do, so so that could be some touch point. Could be interesting. Actually, to whoever asked the question about the zero knowledge proof caches, I actually don't know what that is, but thanks. I want to learn about that. It sounds interesting.
Alex, we just got one more question from.
Oh, please. Yeah.
If we still have a couple of minutes. So what are the main limitations of Neuro-LENS when compared with end-to-end neural models?
Some limitations are, well, there's no end-to-end training which includes both symbolic and neural components. Also, I think, especially for mainly for the detection object detection use case, one big caveat is that the performance of the whole method really depends on the performance of the object detection. Because of course, if an object is not detected, then you're not going to be able to extract attributes, and it's just not going to be considered at all within the approach. So I think those are the two main limitations.
Okay. One last question. Is there any others, Olga?
No, but that's it for now from the audience.
Oh, we do have one more thing. From Discord.
Oh, in Discord, sorry. I need to monitor both. Okay. It's the comment about the question about the zero cache. I believe it is from this person. It's our old friend. It's asking because though I only caught the last section of the talk, I was concerned about the speed of the logical inference because vehicles have to make decisions quickly. It's just more like a comment.
I mean, it's not like we are predicting the time this next hour, 6 hours, 12 hours. So it's not a matter of, it's not streaming data.
Yeah. This is heavy duty vehicles that cross Europe. So it is important to know when you have to send it to maintenance before a long trip, but you don't need to do it on the spot in the middle of the road. No.
I'm curious, do they use your model, your predictions?
Is it used?
Yes.
No, sadly, no. But maybe in the future.
Very good. Well, we also like this because it's at least the beginning of Neuro-Symbolic being put into the real world. So, and I think that is something we really want to help foment. All right. Well, thank you so much. We're at time, and nice stuff. So, Giulia, Veselka, Elena, questions we haven't gotten to, that'd be great. And otherwise, no more Neuro-Symbolic Wednesdays until August 6th and 7th. So we'll see everyone there. We tend to get thousands of registrants. It should be a fun meeting. Lots of good stuff. And big name speakers and so on as usual. Okay. Thanks everyone. See you in some weeks. Take care.
Thanks for having me again.
Thank you.
Thank you.